All right, so the real question is, why do it this way for simple things like circles and ellipses? And the answer to that is really you probably wouldn't. But the next example is really the one that's going to be kind of the culmination of this whole thing. It's why we would even want to try and do something like this. And this example will take the longest of all of them because it can take a little bit of time to develop, but I promise you it is worth it in the end. All right, so example 3. Let's say we've got a whole bunch of dots all over the place. And honestly, for you guys, it doesn't really matter where you put your dots. I'm just putting a bunch of random dots all over the place. So I am going to connect the dots. Let's connect the dots. Let's make this fun. That one goes to there, to there, 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 up to there, maybe over to here. Yeah, that looks good. So by connecting all those dots, I do have now an enclosed region. And we're going to say that that's our region D. So it is enclosed. And I'm going to need to make sure that we transverse this thing the correct way. So it's got to go like this. Well, as you can imagine, I mean, this is a whole bunch of linear pieces which make up this thing. It is a polygon. I mean, that's what it is. This thing is a polygon. It's a polygon of, what do we got? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 sides, if I counted that correctly. We got a polygon of 9 sides in this case. So if I were to take the line integral of every single one of these pieces, which I could do, be kind of a pain to do it, but I could do it, and assuming that all of this stuff added up to 1, which we're going to show that it can, then we would find the area of D. So if I were to start labeling this, maybe this is C1, this is C2, C3, all the way around. I'm not going to label every single piece, but that's the idea. You would get all the way around. That means that what I would have here is I would have some kind of a point. We're just going to call this point x1, y1. This point up here would be x2, y2. And then as you can imagine, we're going to go around x3, y3, and so on, all the way up till, and I'm going to label this last one over here, while it would be our 9th one in this case, I believe, we're going to call it x sub n, y sub n, because it could be for any number of possible points here. If I wanted to find C, just C in general, C, try that again, C is going to be all of the C's added up, C1 plus C2 plus C3 plus all the way up to C sub n. Alright, so what we're going to try and do is we are going to try and find, using Green's theorem in reverse, the line integral of all of our C's of x dy minus y dx, well, 1/2 of that. So we're going to need to parameterize this, and this is a little bit more challenging to think of in the beginning, but it's not really difficult because of the fact that all of these things are linear. So it's not that hard to see. If we're going to parameterize this, x, well, x is going to start with, we're just going to go with, we're going to start with this particular piece right here. And then we're going to show how to connect this to all of them. So x is going to start at x1, and it's going to go to x2, which means that we really have to find the difference between x1 and x2 in order to find what gets multiplied by t. Well, the difference between x1 and x2 is simply going to be x2 minus x1 times t. So that's the linear piece from the x's, and the y's are going to be similar. Y is going to start at y1, and then it's going to add the difference between the two y values, between y2 and y1, times t. And that's how you'll parameterize it. All right, so let's go ahead and start writing out the integrals. Now, I do want to warn you that this is going to take a little space, so you might want to write a little bit smaller on your page. So the first one is 1/2. Now, remember that since we parameterize these as linear, each piece is going to go from 0 to 1. And again, we're only dealing right now with C1, so this is C1 right here. All right, so we are going to do x, which is x1 plus the quantity x2 minus x1 times t times dy. And dy is the derivative of this guy right here. I'm actually going to write these out. So dy, oops, not dy over anything, just dy. So dy is going to be the derivative of this. Well, y1 is a constant, so that's gone. y2 minus y1 is also a constant in front of t, so the derivative of that is just going to be y2 minus y1. It's just like having a 5 in front of the t. The derivative of 5t would be 5, so the derivative here is y2 minus y1. The same idea with the dx part. The derivative of x with respect to t, again, is going to be, oh yeah, there's a dt there, sorry. The derivative of x, again, the derivative of x1, that's a constant, it's gone. The derivative of the part that's attached to the t is just going to be the coefficient, so it's x2 minus x1 dt. Alright, so now we have what we can plug in here. And again, I'm going to pull the dt's all the way off to the right with our integral just to save a little bit of space there. So then we're going to have, so where are we at here? dy. So that's y2 minus y1. And again, I'll pull the dt off to the right. Minus y. Y is y1 plus y2 minus y1 times t times dx, which is, that doesn't look good. Whoops. That's going to be, where are we at? x2 minus x1. And then the whole thing here is dt. There we go. All right, let's do a little bit of simplification here. Actually, no, let's not do a simplification. It's actually going to be easier not to. You just have to remember what parts are constant here and what parts are you're actually taking antiderivatives with respect to. So we are going to separate this, not physically, but we are going to separate this into two separate integrals when we do this. So the 1/2 is just going to stay a half. Now I'm going to take the antiderivative. So this y2 minus y1, which is really the, here, let me label this actually for you guys just to make sure you see what this is. This was your dy, this was your dx, this right here was y, this right here was x. And that was from the original x dy minus y dx. The y2 minus y1, or the dy part, is actually just a constant. So it's not going to have any effect on the antiderivative. So I'm just going to leave that as y2 minus y1 and then the antiderivative of the inside of this, well, the antiderivative of x1 with respect to t is just going to be x1t. x1t. Now the antiderivative of the x2 minus x1 times t part, well, t is already there, so we're going to raise that by 1. That'll be t squared, and then we're going to divide it by 2. So what you're going to get here is x2 minus x1 over 2 t squared. And then we're going to do the same idea over here. This x2 minus x1 is just like a coefficient. It's just a constant, so we're just going to bring it out to the front because it's being multiplied. I could have distributed these things through, by the way, and you'd see it doesn't have any effect on it other than to be a constant coefficient, but it's just easier to leave it on the outside for now. Antiderivative of y1 is just going to be y1t. antiderivative of y2 minus y1 times t is going to be pretty much what we did before. It'll be y2 minus y1 over 2 t squared. And we're going to evaluate that from 0 to 1. And again, keep in mind what you're actually plugging in the zeros and the ones for. So let's plug in 1. 1 gets plugged in for t. So again, y2 minus y1 stays there. If I plug 1 in for t, I get x1 plus, plugging a 1 into the t squared also gives me 1, so it's x2 minus x1 over 2. And then minus x2 minus x1 stays there. And then plugging 1 in for the t, I get y1. Plugging 1 in for t squared, I just get y2 minus y1 over 2. And then minus, well, if I plug 0 in for t, I'm going to get 0 on each part of the these parentheses right here. I'm going to get 0 in here, I'm going to get 0 in here, times the constants out front still gives me 0. So the 0, fortunately, is gone. So that's what we're down to so far. So now I'm going to simplify a little bit of what's inside of here. So that's still going to be y2 minus y1. Now this is going to be x1 plus 1/2 x2 minus 1/2 x1. I'm going to be able to combine these two things in a second. Minus x2 minus x1 times y1 plus 1/2 y2 minus 1/2 y1. And I'm going to be able to combine those two pieces because they are the same. So we'll have 1/2 y2 minus y1 times, looks like what we're going to get here is a 1/2 x1 plus 1/2 x2 minus x2 minus x1. Same deal over here. We're going to get a 1/2 y1 plus 1/2 y2. I now have a 1/2 in common there. I have a 1/2 in common here. I can pull those 1/2s out to the front. And remember, you're factoring a 1/2 out of each one of these things, so it's not like I'm going to be factoring an extra 1/4. It's 1/2 being pulled out of each one. So I'm factoring that 1/2 out to the front, which will give me a 1/4 total because of the extra 1/2 out in the front. And then I have y2 minus y1 times x1 plus x2 minus x2 minus x1 times y1 plus y2. Getting there, almost done. I do have to FOIL this stuff. So we're going to go ahead and distribute everything through. So we're going to get, let's see, y2 times x1. I am going to try and write them in the correct order if I can. x1, y2. Outer is y2 minus x2. So that's x2, y2. Inner minus x1, y1. And then last, minus x2, y1. And then let's see if we can do this. It's going to be minus, because of the minus sign in the middle, x2, y1. Outer, minus x2, y2. Inner is now going to be plus x1, y1. And last is going to be plus x1, y2. Hopefully I got all those straight. I think I did. Alright, so let's see what we can get rid of now. So I've got x1, y1. Whoops. x1, y2. Do I have another x1, y2 somewhere? Yes, I do. So I'm going to have two of those. I can't get rid of those. x2, y2. I got a negative x2, y2 and a positive, go away. and a positive x2, y2. I've got a negative x1, y1 and a positive x1, y1. Those are gone. And then I've got a minus x2, y2, but another minus x2, y1 and another minus x2, y1. So those are going to have to stay. So it looks like we're going to have 1/4 of 2 x1, y2s minus 2 x2, y1. But then, of course, I can pull the 2 out to the front, so that's going to give me 1/2 of x1, y2 minus x2, y1. So, I am almost out of room, but we're doing okay because we really don't need the whole thing. What we have is that the line integral for C1 is going to be 1/2 of x1, y2 minus x2, y1. And what I want to show you is, so that's the first component of x times the second component of y minus the second component of x times the first component of y. So if we kind of go back up to our polygon, we are taking 1/2 of this times this minus 1/2 of this times that. Or you can pull the 1/2 out to the front. So it's going to be, here, let's do this in a different color. Nope, wrong color. So it's going to be x1, y2 minus x2, y1. And then hopefully what you can see is that this pattern would keep going if we did C2, which we're not going to work out here. I'll just show you that if we did C2, and I'll write out what the next ordered pair would have been, x3, y3. If you follow the same pattern, to go from C2 to C3, it's going to be x2, y3 minus x3, y2. And it's going to be 1/2 of that. And you can do that all the way around. So you would basically do that 9 different times. Now, do you have to do this entire integral every single time? No. The whole point is what I just developed for you guys, is that this is what you would get for C1. So if I wanted to do C2, line integral over C2 would be 1/2 of x2, y3 minus x3, y2. And then you could do that exact same thing for every single one of them. So as long as you know what the x and y values are of all your ordered pairs, and you would have to know that obviously, you could find the area of this polygon by adding them all up. So add all integrals over C, and you would get area of the polygon. And again, this is much easier to do than if you were to try and algebraically figure out this area. I mean, you could probably do it. You could create, maybe a triangle. See if I can at least kind of sketch. You could create like a triangle here, and then maybe a triangle here, and you could try and figure out all the areas of these different pieces of the polygon. That would be a real pain, though, because of the fact that you'd have to probably use a bunch of laws of sines and cosines and things like that to figure it out. So let's get rid of those because those really are not part of it. But there you go. The one thing I can tell you is that this does make this process much, much easier to find areas of polygons.